It's almost unbelievable, but a large turbine engine on a jetliner can gulp down the entire volume of air in a standard living room in like less than a second.
Wow.
Think about that. It really highlights the immense need these incredible machines have to, well, breathe.
Yeah.
And that's exactly what we're diving into today, the fascinating and really critical world of aircraft engine induction and exhaust systems.
That's right. From the fundamental ways reciprocating engines draw in air and expel exhaust, all the way up to the more sophisticated solutions in turbine engines.
Right.
Efficiency and safety in these systems are just paramount. We're drawing on some detailed technical info here, and our aim is to give everyone a clear, insightful understanding of how these engines manage that essential airflow.
Okay, let's unpack this then. Starting with reciprocating engines, which maybe many of us are a bit more familiar with. The source material lays out the basic system pretty clearly, beginning with the air scoop.
Yeah, the scoop.
Yeah.
That often kind of unassuming opening you see on the engine cowling. That scoop, like the one shown in Figure 3.1, is strategically placed to capture the maximum possible free-flowing air. From there, the air travels through ducting.
Okay.
And a really crucial point in this journey is the inlet filter. It's frequently located within the carburetor heat box. You can see it in Figure 3 too.
Ah, the filter. That's the engine's main defense against stuff in the air.
Precisely. Airborne particles, dust, grit, you name it.
And once it's cleaned, this vital air makes its way to the fuel metering device, which could be a carburetor or a fuel injection system.
Depending on the engine's design, yeah.
Now, a key aspect the source highlights is manifold pressure. Can you explain what that is and why it's important?
Sure. Manifold pressure, usually measured in inches of mercury, or Hg, is basically the pressure of the air inside the intake manifold.
Okay, so after the throttle.
Right, after the throttle, on its way to the cylinders. It's a direct indicator of how much air the engine is taking in, and consequently, it's a primary control over the power the engine produces.
Got it. So, more pressure, more power, generally speaking.
Generally, yes.
Our chapter then explores different setups for these induction systems, specifically updraft and downdraft arrangements. What's the main difference there?
The core difference is really just the direction the air flows through the system. In an updraft system, like in Figure 3.3, air usually flows upwards towards the cylinders.
Okay.
They often use something called a balance tube to equalize the pressure distribution among the intake runners. That's particularly important in carbureted engines, to make sure a consistent fuel-air mix reaches each cylinder.
And downdraft.
Downdraft systems like in Figure 3.4, they typically offer a more streamlined airflow path across a wider range of conditions. Generally leads to smoother, more efficient engine performance. Works well for both carbureted and fuel-injected engines, where the fuel's added right at the intake port.
Okay, interesting. Now, let's focus on the carburetor induction system itself. Figure 3.2 shows it clearly. Normal airflow comes in, passes through the filter, then into the carb. Simple enough. But then there's the vital function of carburetor heat. Why is that so critical?
Carb heat. It's an absolutely essential anti-icing measure. See, as air speeds up through the carburetor's venturi, the pressure drops.
Right, the Venturi effect.
Exactly. And that pressure drop can significantly lower the air's temperature. If there's enough moisture in the air, even if it's not freezing outside, that temperature drop can cause ice to form.
Inside the carburetor.
Right inside. It restricts airflow, potentially causing power loss or even engine failure. Figure 3.7 shows where it can build up.
Nasty stuff.
Yeah. So the carb heat system, shown in Figure 3.5, lets the pilot redirect warm air, usually from around the engine's exhaust manifold, into the carburetor to prevent or melt that ice.
So it's really about managing that risk, that constant threat of icing. It highlights how much atmospheric conditions matter.
Absolutely. And it shows the ingenuity needed in design for reliability.
And that's a pilot-controlled system, right? From the cockpit.
Yes, pilot-controlled.
The source also mentions an alternate air door. What's that for?
That's a clever little safety mechanism. If the normal air path gets blocked, maybe the filter gets completely clogged or iced over.
Okay.
The engine section can automatically pull open this spring-loaded door. It allows the engine to draw air from an alternate source, usually unfiltered air, from inside the engine compartment.
So it's a backup. Keeps the engine from suffocating if the main inlet is blocked.
Exactly. A crucial backup.
Going back to the air filter itself, Figure 3.6 gives a good look. It's not just a simple screen, is it?
No, not at all. A typical filter has an aluminum frame holding a deeply crimped screen. That crimping maximizes the surface area exposed to the air.
Makes sense. More area to catch particles.
Right. And different materials are used, paper, foam. The key thing, stressed in the source, is regular servicing per the manufacturer's specs.
Because a clogged filter
Severely restricts airflow, impacts power, can even make starting tough.
The chapter also touches on RAM air intake. Sounds like using the plane speed to help out.
That's precisely it. By putting the air intake in the slipstream, the airflow from the propeller, and the plane's movement, the design uses that forward speed to effectively force more air into the system.
Creates a slight pressure increase.
Yeah, a slight increase. It's like giving the incoming air a running start.
So a little performance boost, but I guess it depends on airspeed. Less effect at slow speeds.
Definitely more effective the faster you go.
Now, we can't talk induction without really digging into icing. The source details 3 main types.
Yes, induction icing is a major hazard. It can happen even in clear air if humidity is high.
Really? Even without visible moisture?
Yep. So first you have impact ice. That's supercooled water droplets hitting surfaces like the scoop or filter and freezing on contact.
Okay.
Then there's fuel evaporation ice. That's caused by the temperature drop when fuel vaporizes in the carburetor, the same cooling effect we mentioned earlier.
Right, the venturity cooling.
And finally, throttle ice. This can form right around the throttle plate, especially during part throttle operation, because of the low pressure and temperature right there. Figure 3 to 7 shows these spots really well.
And card heat is the main defense against all of these.
Absolutely. Warming the air prevents ice forming or melts what's already there. But, and this is important, the source rightly points out that using carb heat when you don't need it can cause problems too.
Right, like power loss.
Exactly. Using carb heat when there's no icing risk reduces the air density. That makes the fuel-air mixture richer, leading to a noticeable drop in power.
And potentially detonation.
There's even a risk of detonation with very high intake air temps, especially during critical phases like takeoff. So you only want to use it when icing is actually a risk.
Use it judiciously.
Precisely. The source also flags a specific scenario prone to throttle icing. Glide descents with fixed-pitch propellers.
Oh. Why is that particularly bad?
Well, in a glide with a fixed-pitch prop, the prop keeps windmilling, right?
Oh.
So the engine is still drawing in a fair bit of air, even with the throttle closed down low.
Okay.
That increased airflow, combined with the partly closed throttle, creates a really high-velocity, low-pressure zone right at the throttle valve. Prime conditions for ice.
Ah, I see. And controllable pitch props help how?
With a controllable pitch prop, you can maintain a higher BMEP that's brake mean effective pressure, basically the average pressure in the cylinders, which allows for a larger throttle opening at lower RPM. Less restriction, less temperature drop at the throttle.
Makes sense. Okay, the source then shifts to filtering again, emphasizing how bad dust and dirt are for the engine.
Yeah, it paints a pretty stark picture. Dust, abrasive particles, they act like sandpaper inside the engine.
Wearing down cylinder walls, piston rings.
Exactly. Contaminates the oil, accelerates wear on bearings, gears. In really bad cases, it can even block oil passages. Catastrophic failure territory.
So good filters are obviously essential. What about operations in really dusty places?
Right. For those conditions, some aircraft have alternate induction inlets with special dust filters. These systems often use things like louvers or changes in airflow direction to try and separate out the heavier dust particles before they even hit the filter media.
Clever, but even the filters themselves aren't immune to everything, right? Filter icing?
Yes, that's a concern too. If a filter gets soaked with rain and then you climb to freezing altitudes, the filter itself can freeze over, blocking airflow.
So what's the fix for that?
Some systems have spring-loaded filter doors. If the filter gets too restricted, suction pops the door open, bypassing the iced filter like the alternate air door we talked about.
Another backup.
Or they might use ice guards, basically coarse mesh screens placed before the main filter. They catch the bigger ice particles, letting drier air pass through to the main filter.
Okay, so with all these components, scoops, ducts, filters, doors, carb heat, regular maintenance is obviously key. What are the main things to look for?
Routine checks should always look for cracks, leaks, and make sure everything's securely mounted. Keeping the system clean is critical. No forgotten rags or paper blocking things up.
Right.
And for the filters themselves, regular checks, cleaning, proper oiling if it's an oil-wetted type, or replacement as needed. Like we said, a dirty filter really hurts power and starting.
The source also mentions a critical safety procedure, extinguishing engine fires during startup.
Absolutely critical. You should always have a designated fire guard with a CO2 extinguisher ready during engine start.
And they need to know where the intake is.
Yes, precisely. So they can direct the CO2 right into the intake if a fire flares up. The first reaction if a fire starts during cranking is actually to keep cranking.
Try to suck the flames in.
Yeah, try to draw the fire into the combustion chamber. If that doesn't work quickly, abort the start and extinguish it externally.
Got it. Finally, for recips, Figure 3.8 offers a troubleshooting guide. Looks like common issues and causes.
Exactly. Obstructions, leaks, loose ducts, dirty filters. The usual suspects. It's a concise guide for basic diagnostics.
Okay, that's a good overview of the basics. Now, let's talk about boosting that intake pressure, supercharging.
Right. This becomes essential when you start flying higher, where the air gets thin.
This is where things get really interesting, yeah. The source explains that less dense air at altitude means less power. Supercharging fights that. It differentiates between normalizing systems and true supercharging or ground boosting. What's the difference?
Good question. Normalizing systems are basically designed just to compensate for the pressure loss as you climb.
Ah.
They bring the manifold pressure back up towards sea level pressure, but typically don't exceed about 30 inches of mercury.
So just regaining lost power.
Exactly. True supercharging, or ground boosting, goes further. It intentionally increases manifold pressure above ambient sea level pressure, so you get more power than a naturally aspirated engine, even down low.
Ah, okay, so one compensates, the other enhances.
You got it.
And the source broadly categorizes these systems as either internally driven or externally driven. Externally driven meaning turbo-supercharged.
Correct. Internally driven superchargers, like in Figure 310, are mechanically geared to the engine crankshaft. They usually compress the fuel-air mixture after the carburetor. These were common in older, big radial engines.
And turbo-superchargers?
Turbo-superchargers, or just turbochargers, are externally driven. They use exhaust gas energy that would otherwise be wasted to spin a turbine.
Okay.
That turbine is connected to a compressor, which packs more air into the engine before the fuel is added.
The chapter mentions that even with internally driven superchargers, controlling air temperature is still crucial. Why is that?
Well, just like naturally aspirated engines, you need the fuel-air charge warm enough for good fuel vaporization and distribution.
Right.
But the act of compressing the air heats it up. Too hot, and you lose volumetric efficiency, or worse, risk detonation. So these systems often needed ways to warm or cool the charge as required.
A balancing act. Figure 310 shows a basic internally driven system. Ram air, carb, supercharger, then the gauges. Seems straightforward.
Pretty much. And notice, the source points out a significant temperature drop across the carb, maybe 50 degrees Fahrenheit, just from fuel vaporization.
Wow, that much.
Yeah. And getting that atomized fuel evenly distributed to all cylinders is a key challenge, especially in multi-cylinder engines.
Figure 311 shows something called a distribution impeller, mostly in radials. Looks like it's on the crankshaft.
It is. It spins at crank speed. Its main job isn't really boosting pressure much. It's more about physically hitting those fuel droplets as they come through.
Breaking them up.
Exactly. Breaking them into finer particles, creating a more uniform, homogeneous mixture. Helps distribution, especially during quick throttle changes or in the cold.
Okay, so that's for mixing. When we talk about actually increasing pressure, that's the supercharger blower impeller. Different thing.
Yes, totally different. Unlike the distribution impeller, the blower impeller is gear-driven. It spins much, much faster than the crankshaft.
To generate the pressure.
That's where the real boost comes from in those systems.
Right. Let's move to turbo superchargers then. Figure 312 gives a good overview. Harnessing that exhaust energy.
Precisely. Turbochargers use the engine's hot exhaust gas. It's directed onto a turbine wheel, spinning it incredibly fast.
And that turbine drives.
A compressor impeller, connected by a shaft. The impeller sucks in ambient air and compresses it before it goes to the engine's intake. And to be a true supercharger, it has to be able to boost manifold pressure above that standard sea level pressure, about 30 inches Hg.
Figure 313 shows the main parts. Compressor assembly, turbine wheel assembly, shaft bearing assembly, and a baffle.
Yeah, the baffle, or sometimes it's called a cooling shroud. It sits between the super hot turbine housing and the compressor casing.
What's it do?
It directs cooling air towards the bearings, which get incredibly hot. And it also shields the compressor side from the turbine's radiant heat. Keeps the intake air from getting excessively preheated.
Looking closer at the compressor assembly, it speeds the air up first, then converts that speed to pressure.
Exactly. The impeller blades accelerate the air outwards at high velocity. Then the diffuser, which has specially shaped vanes, slows that fast-moving air down.
And slowing it down increases the pressure.
Right. Converts kinetic energy velocity into static pressure.
And the turbine wheel assembly? That's where the exhaust magic happens. Figure 314 shows it, and 315 highlights the wastegate valve. Crucial component.
Absolutely critical. The exhaust gases flow from the cylinders into the turbine housing, hit the turbine blades, make it spin. That spin drives the compressor.
Okay.
Now, the wastegate is basically a bypass valve. It can divert some, or even most, of the exhaust around the turbine, straight out the exhaust pipe.
Why bypass it?
To control the turbine speed. By controlling how much exhaust hits the turbine, you control how fast it spins, which directly controls how much boost the compressor makes. It's the boost regulator.
So wastegate closed means maximum exhaust through the turbine, maximum boost. Wastegate open bypasses exhaust, less or no boost.
You've got it.
The source then differentiates again. Normalizer turbos versus ground-boosted systems. Normalizers just compensate for altitude.
That's right. Normalizing turbochargers, like in Figure 316, are just designed to maintain sea level power as you climb. They generally don't boost above 30 inches HG and might only really kick in above a certain altitude.
And ground-boosted systems, figures 317, 318.
They're designed to provide boost right from sea level up to their critical altitude. They can boost manifold pressure well above 30 inches, often around 40 inches or so. Big power increase, even low down. They usually have filtered ram air intakes and alternate air doors too, like we saw in the non-turbo recips.
Our source mentions engine oil is almost always used to control the wastegate actuator. How's that work?
Pressurized engine oil is sent to the wastegate actuator, which is just a piston or diaphragm, mechanically linked to the wastegate valve.
So oil pressure moves the valve.
Exactly. By precisely controlling the oil pressure going to the actuator, the system controls the wastegate position and therefore the boost level. Plus, that oil also cools and lubricates the turbo's high-speed bearings.
Figure 318 shows a typical ground-boosted system schematic. Highlights 3 key parts for automatic control. The exhaust bypass valve assembly, that's the wastegate, right? The density controller and the differential pressure controller. Sounds like a complex balancing act.
It is. They all work together. Wastegate position determines exhaust flow to the turbine. The density controller senses air density, pressure, and temperature, and primarily limits the maximum manifold pressure below the critical altitude when you're at full throttle.
Okay. Prevents overboosting at low altitudes.
Right. And the differential pressure controller, well, it works across the whole throttle range. It stops the density controller from always trying to give max power, and it also helps prevent something called bootstrapping.
Bootstrapping. Sounds unstable.
It is. It's basically an uncontrolled oscillation. A small change in power or conditions causes the turbo system to sort of chase its tail, with manifold pressure drifting up and down unstably. Think of audio feedback, that screech.
Yeah.
Kind of like that, but with air pressure. The differential pressure controller helps damp those oscillations out. It's different from overboost, which is just exceeding the pressure limits, potentially damaging the engine. Some systems have a separate pressure relief valve just for overboost protection.
The source also mentions overshoot with turbos.
Related, but usually less severe. Overshoot is a temporary surge or dip in manifold pressure when you make quick throttle changes. The system just can't react instantly because the turbo has inertia. It takes time to spin up or down.
So smooth throttle movements are key.
Exactly. Make deliberate changes, give the system a moment to stabilize.
The chapter then briefly mentions different controller types, VAPC, sloped, absolute pressure controllers, figures 321, 322, just different ways to manage the boost.
Yeah, basically different mechanical and pneumatic strategies using aneroids, bellows, oil valves, etc. to fine-tune the turbo's output across different conditions and prevent overboost or underboost depending on altitude and throttle.
And figure 320 shows an aftercooler. What's its job?
Okay, so compressing air makes it hot, right?
Yeah, right. Physics.
The aftercooler, sometimes called an intercooler, is just a heat exchanger. It cools that hot compressed air after it leaves the turbo and before it goes into the engine cylinders.
Why cool it back down?
Cooler air is denser. Denser air means more oxygen molecules per volume, which means you can burn more fuel and make more power. Plus, it reduces the risk of detonation. Better performance, better reliability.
Makes sense. And finally, for supercharged systems, figure 323 is another troubleshooting guide. Failure to reach critical altitude, surging, wastegate issues.
Exactly. A quick reference for diagnosing common turbo system problems.
All right. Now for the really big leagues. Turbine engines. How do they handle the massive amounts of air they need? Their inlet systems must be totally different.
Oh, absolutely different scale. The source starts by stressing the main design goal. Deliver a smooth, distortion-free flow of air in the huge quantity needed right to the compressor inlet, often helped by inlet guide vanes, as you see in figure 324.
Distortion-free. Why is that so important?
because inconsistent or turbulent airflow can cause compressor stall. That's where the airflow breaks down over the compressor blades. It can even reverse flow momentarily. Very bad for the engine. Can also lead to excessive temperatures downstream in the turbine section.
Okay.
And interestingly, the inlet duct itself is usually considered part of the airframe, not the engine. But its performance critically affects the engine's thrust and efficiency.
And the sheer volume of air. Just way beyond a piston engine.
Orders of magnitude more. So the air entrance has to be correspondingly huge.
Inlet efficiency seems even more critical here.
Hugely critical, especially at high speeds. Any energy loss or flow disruption in the inlet gets magnified as the air goes through the engine. And the design varies a lot. Turboprops, turboshafts have smaller inlets compared to the giant mouths of big turbofans.
And some smaller turbines use inlet screens, figures 328, 329, for FOD protection.
Yes, foreign object damage. Screens can protect delicate compressor blades, but we'll come back to the pros and cons of those.
As the aircraft speeds up, you mentioned ram recovery earlier. That helps turbines too.
Oh, yes. As the plane flies faster, the incoming air gets compressed just by ramming into the inlet duct. This recovers some of the air's total pressure.
So the faster you go, the more pressure you deliver to the compressor.
Up to a point, yes. It helps boost the engine's pressure ratio and airflow, offsetting some potential losses at higher Mach numbers.
So the inlet duct needs to recover pressure, deliver smooth, uniform airflow, and do it all with minimal drag.
That's the challenge. Pressure losses come from friction inside the duct and any bends or sharp turns. Smooth flow is king.
Some turning is okay for smaller engines to keep the nacelle compact.
For lower airflow engines, yes, some gentle turning is acceptable to reduce drag. But for big, high airflow turbofans, you really want a straight shot into that fan for even distribution. Engine location, speed range, altitude, even aircraft attitude, all influence the final inlet design.
Figure 326 shows inlet ducts acting as diffusers. What does that mean for the air?
A diffuser is basically a duct that widens. As the air flows through this widening passage from the inlet lip towards the compressor, it slows down.
Slows down. But doesn't that hurt?
No, because as the velocity decreases, the static pressure increases. You're trading speed for pressure, converting kinetic energy to potential energy, which is what the compressor wants, higher pressure air.
Okay. The source then talks about different inlet shapes. Divided entrance ducts, figure 325, common on military jets.
Yes, you see those a lot, inlets on the sides of the fuselage, or maybe wing roots, often needed when the cockpit sits low and forward.
Challenges there.
Getting enough scoop area without creating too much drag is tricky. Inside, the principles are the same. Keep it short, smooth, minimal bends. Sometimes they use turning vanes inside the scoops to straighten the flow out before it hits the engine.
Then there's the variable geometry duct, figure 327. That sounds complex.
It is essential for supersonic aircraft. The big problem is the air must be subsonic when it hits the compressor face.
Even if the plane is supersonic.
Exactly. So as the aircraft goes supersonic, these ducts physically change shape internally. They use movable ramps or wedges to slow the incoming supersonic air down progressively back to subsonic speeds before it reaches the compressor. Some even have bypass doors to dump excess air.
Wow. The chapter also mentions using shock waves deliberately inside supersonic inlets. That sounds bad.
It seems counterintuitive, right? But in supersonic flow, creating controlled shock waves, these thin regions where pressure, temperature, velocity change abruptly, is actually a way to diffuse the flow.
Like aerodynamic brakes.
Exactly. The shock wave helps slow the air down. Sophisticated inlets use a combination of changing geometry and carefully positioned shock waves to manage the supersonic airflow efficiently with minimal energy loss.
We mentioned inlet screens earlier. The source digs into the pros and cons for turbines now.
Right. Screens can offer some FOD protection, especially for engines with, say, aluminum compressor blades, which are more vulnerable.
But the downsides?
They cause a pressure drop in the inlet, which hurts performance. They're prone to icing. And the screen itself can fail, potentially causing more damage than the FOD was meant to stop.
So big turbofans usually don't use them?
Generally not. Their big fan blades are usually tougher steel or titanium. The risks often outweigh the benefits. Some planes have retractable screens. They'll use just for takeoff and landing when FOD risk is highest, then retracted in flight.
Figures 330 and 331 show bell mouth inlets. Very smooth, flared shape. What are they for?
Mostly for engine testing and test cells. That super smooth bell shape is designed for almost zero aerodynamic resistance.
So you get really accurate performance data.
Exactly. Measures thrust, fuel burn, etc., without the inlet duct affecting the numbers. You'll see probes sticking into them to measure intake pressure and temp precisely. You might occasionally see them on some helicopters too, but mostly test cells.
Okay. Turboprops and turboshafts. Figures 332, 333. Unique challenges because of the propeller and spinner.
Yeah, the prop drive system complicates things. Ducted inlets are usually best for turboprops. Many have anti-icing, often electric heating elements in the inlet lip,
Deflector doors, too.
sometimes to divert ice or debris. And conical spinners are common to prevent ice buildup right on the spinner. How the spinner interacts aerodynamically with the inlet is really important for performance.
Right. Finally, turbofan inlets. Figures 334, 335. The big fan right at the front is key.
Yes, in high bypass fans, that huge fan is right out front. The inlet cowl forms the main path into it. Because the fan itself is so efficient, the inlet duct design can be fairly conventional, low loss.
And the fan helps with FOD.
It does, actually. It tends to sling ingested debris outwards centrifugally, away from the core engine. Anti-icing is usually done with hot bleed air from the compressor, piped to the inlet lip.
And things like abradable rub strips.
Yeah, inside the cowl. Allows the fan blade tips to rub slightly during maneuvers without damage. And lots of sound-absorbing material in the nacelle to quiet down that fan noise.
Figures 336 and 337 show the dual airstream of these high bypass fans. Most thrust comes from the bypass air.
It does. The air going around the outside of the core engine, accelerated by the outer parts of the fan blades, that's the secondary or bypass flow, makes up maybe 80% of the total thrust.
And the rest goes through the core.
Right. The air through the inner part of the fan is the primary or core flow. Goes through the compressor, combustor turbines like a regular jet engine.
How does the fan exhaust get out?
Two main ways. Either short ducts right behind the fan, creating separate hot core and cold fan streams, or in ducted fan engines, the fan air is ducted all the way back and mixed with the core exhaust before exiting a common nozzle.
Fascinating stuff. Okay, let's switch back to reciprocating engines now. How do they get rid of the hot exhaust gases?
Right, the exhaust system. The source starts by stating its main job, scavenging those hot, noxious combustion products safely away from the engine, the airframe, and importantly, the occupants.
Safety first.
Absolutely.
Yeah.
While they can do other things, like provide cabin heat or carb heat, the number one job is safely getting rid of high-temp, corrosive, potentially lethal gases. Modern systems are built tough to handle this with minimal maintenance.
The chapter outlines two main types for recips: short stack or open systems and collector systems. Where do you see each?
Short stacks are typically on non-supercharged, lower power engines where noise isn't the biggest issue. Just short pipes straight off each cylinder. Simple.
And collector systems.
Used on most larger non-supercharged engines and pretty much all turbo-supercharged engines. You need a collector system for a turbo, right? To gather all the exhaust to spin the turbine.
Makes sense.
Collector systems usually have individual pipes, headers, leading into a common manifold or collector ring, then a single outlet. They do create a bit of back pressure, but the power gain from turbocharging far outweighs that small loss.
Figure 338 shows a typical collector system on a horizontally opposed engine. Looks like a maze of pipes.
It is. You've got downstacks from each cylinder head feeding into collector tubes along the sides. Then those often lead to exhaust ejectors poking through the firewall.
Ejectors.
Yeah, they're tapered to create a Venturi effect. As the exhaust rushes out, it pulls cooling air through the engine compartment, kind of like an augmenter tube action. And figure 339 shows a cabin heater shroud wrapped around one collector using exhaust heat.
Figures 340, 341 show a radial engine collector ring. More complex circular setup.
Yes, for say a 14-cylinder radial, it's usually a welded steel ring made in sections. Each section collects from maybe 2 cylinders. They often get bigger towards the outlet tailpipe.
How does it attach?
Bolted to the engine, partly supported by slip joints at the exhaust ports. And they usually have a telescoping expansion joint built in.
For heat expansion.
Exactly. Allows for thermal growth and contraction, and makes it easier to remove sections without taking the whole tailpipe off.
The source also mentions a combined manifold and augmenter system on some radials for extra cooling.
That's right. Exhaust manifolds collect gases from cylinder groups, then dump them into augmenter tubes. These augmenters have a bell mouth shape at the front to create a really strong Venturi effect, pulling a lot of cooling air over the engine cylinders. Some even had adjustable vanes in the tailpipe to control the airflow and engine temp.
Given the heat and corrosive gases, maintenance must be super critical.
Absolutely. Any exhaust system failure is serious. Potential for CO poisoning, power loss, even fire. Regular, thorough inspections are vital.
What are the telltale signs of trouble?
Black soot around gaskets or connections is a classic sign of a leak. needs checking immediately.
Figure 342 shows key inspection areas. Looks like you need to check everything.
Pretty much. Look over all external surfaces for cracks, dents, missing parts. Check welds, clamps, supports, slip joints, flanges, gaskets. Pay attention to dents or low spots, could be thinning or corrosion.
The source mentions probing suspected areas.
Yeah, gently, with like a blunt ice pick, just to check for weakness. And a big no-no, don't use galvanized tools or lead pencils on exhaust parts.
Why not?
The zinc or lead can actually soak into the metal at high temps and weaken it, causes intergranular corrosion.
Wow. What about checking internal parts, like baffles inside mufflers?
Often need some disassembly. If you can't see inside, a common trick is to plug all openings but one, put in a very low pressure of air like 2 psi, and submerge the part in water. Bubbles show leaks, even internal ones.
And daily checks.
Just a visual scan of the exposed parts for obvious cracks, major leaks, loose clamps.
The source then details specific failures. Mufflers and heat exchangers, figure 343. CO poisoning is the big risk here.
Yes, very much so. A lot of failures are cracks in the thin walls of the heat exchanger surfaces, the parts used for cabin or carb heat.
So exhaust leaks into the clean heating air.
Exactly. Contains deadly carbon monoxide, often caused by thermal stress heating and cooling cycles, plus vibration fatigue. Failed welds on internal heat transfer pins can also leak. Besides the CO risk to people, exhaust getting into the engine intake can cause overheating and power loss too.
Manifolds and stacks can fail too, often at welds or clamps. Fire and CO again.
That's right. Hot exhaust gas escaping is a direct fire hazard, and CO can sneak into the cabin through bad firewall seals, wing root fairings, door seals, places like that.
And internal muffler failures. Sounds like that hits engine performance directly.
Yeah, if internal baffles or diffusers break or deteriorate, they can block exhaust flow, causes power loss. Often happens due to erosion, carburization from high temps, engine backfiring, or unburned fuel igniting in the exhaust. Blockages can also create hot spots on the muffler, leading to more damage.
What about systems with a turbocharger? Higher pressures and temps must make things worse.
Definitely amplifies the risks. A leak in a turbo exhaust system can be like a high-velocity torch, really damaging.
And coke deposits.
Yeah, carbon buildup. Common issue in the wastegate mechanism. Can make it stick or operate erratically. Sticking closed means overboost, very bad. Coke can also build up inside the turbocharger itself, causing power loss. Periodic decoking is often needed.
Even augmenter systems without heat exchangers need careful checks.
Yes, check alignment, make sure they're securely attached, look for cracks in the tubes. Cracks can still be a fire hazard, or let CO into places it shouldn't be.
Finally, repairs. The source seems to lean heavily towards replacement over repair for exhaust parts. Why?
Repairing exhaust components, especially welding, is really tricky and often unreliable. It's hard to know the exact original metal alloy, especially after it's been heat cycled for ages.
So getting the right filler material is tough.
Very tough. And the metal structure might have changed. If you do weld, you absolutely must keep the original shape. Avoid internal bumps that create hot spots or block flow. Always use the right hardware, new gaskets. Because it's so complex and safety critical, replacing with a new or properly overhauled part is usually the much safer bet.
Okay, makes sense. Now, let's shift to turbine engine exhaust, the nozzles.
Yeah.
How do they shape and direct that high energy flow? Looks like different types for different engines, figure 344.
Absolutely. Turbo shafts, like in helicopters, often have divergent nozzles. They widen out. The goal there isn't thrust. It's just to discharge the gas efficiently while the power goes to the rotor.
Okay, turbofans.
They can have separate nozzles for the fan, bypass air,
Yeah.
the core engine air, or sometimes a mixed nozzle where they combine before exiting.
And turboprops, they have nozzles too, even though the prop makes most power.
Yeah, often called tailpipes. They mainly just discharge the hot gas, but they do provide a bit of thrust, maybe 10–15%, usually just a simple conical or cylindrical pipe with a tail cone inside, supported by struts, often an annular gap for cooling air around the hot inner pipe.
The source mentions probes inside the exhaust duct for pressure and temperature. Why measure those back there?
Essential data for engine health monitoring. Turbine discharge pressure tells you about the turbine stage's efficiency and condition. Exhaust gas temperature, EGT, is critical for watching the combustion process and making sure turbine parts aren't overheating.
Figure 346 shows a convergent nozzle. Narrows down. How does that make thrust?
Basic fluid dynamics. As the hot, high-pressure gas is squeezed through that narrowing passage, its velocity shoots up.
Faster gas out the back equals more thrust forward.
Exactly, Newton's third law. But you can only narrow it so much. Too much restriction can choke the flow elsewhere in the engine. Not enough. and you don't maximize velocity. When the exit velocity hits Mach 1, the speed of sound, the nozzle is choked. Constricting it further can build up pressure inside, adding pressure thrust.
Figure 347 shows a convergent-divergent nozzle. Looks more complex, converges than diverges. Why?
The CD nozzle offers big advantages, especially at high Mach numbers where the engine's pressure ratio is really high enough that exhaust velocity could go supersonic.
How does it work?
The first, convergent part, accelerates the subsonic gas up to Mach 1, right at the narrowest point, the throat. Then the second divergent section allows that now supersonic gas to expand and accelerate further, beyond Mach 1.
So even more velocity, more thrust than just a convergent nozzle could manage.
Exactly. You see these on high-performance supersonic aircraft.
Many jets have thrust reversers. Figures 348, 349. Crucial for braking after landing, right? Especially big, fast planes. Two main types.
Yes, vital for slowing down, reduces runway needed. Mechanical blockage types, often on ducted turbofans, physically deploy blockers like clamshell doors right into the exhaust stream to deflect it forwards.
And the other type?
Aerodynamic blockage, mostly on unducted turbofans. They redirect the fan air forward. They use things like translating cowls that slide back, blocker doors that pop out, and cascade vanes to turn the fan air. Since the fan makes most of the thrust on high bypass engines, reversing its flow gives huge braking force.
And these systems need to be super reliable, no messing with engine operation.
Absolutely. Clear indication in the cockpit of their status, usually actuated by pneumatics or hydraulics. And critically important, they must be mechanically locked stowed during flight and maintenance to prevent accidental deployment.
Military jets often use afterburning. Thrust augmentation, figure 350. Sounds like dumping fuel into the exhaust.
That's pretty much it. Used for a massive, temporary thrust increase, sometimes nearly double the normal thrust. You inject extra fuel directly into the exhaust nozzle, downstream of the turbines, and ignite it.
Needs extra hardware.
Oh, yeah. Needs a flame stabilizer to keep the fire lit in that high-speed flow, fuel injectors, an igniter, and crucially, a variable area nozzle that can open up much wider to handle the huge extra volume of hot gas.
Downsides.
Massive fuel consumption. It's like pouring fuel out the back. Some military turbofans mix bypass air into the afterburner section too, helps the extra fuel burn more efficiently.
Figure 351 shows thrust vectoring, directing the thrust, not just straight back, for maneuverability.
Exactly. Hugely enhances agility, especially for VTOL aircraft or high-performance fighters. The exhaust nozzle itself is designed to pivot or use vanes to direct the thrust stream at an angle up, down, or sideways.
Like the example 20 degrees up or down.
Yeah, that kind of deflection gives much better control, especially at low speeds where control surfaces are less effective.
Engine noise suppression. Figures 352, 353. Big deal near airports. What makes the noise and how do they reduce it?
Main source is the high-velocity jet exhaust mixing violently with the still air around it. Creates intense turbulence. Lower frequency noise travels further, tends to be more annoying.
And noise scales with thrust and velocity.
Directly. Turbofans, especially high bypass ones, are generally quieter than old turbojets for the same thrust because their bypass exhaust velocity is lower.
How do they quiet things down?
Common methods include special nozzle shapes, corrugated edges, multi-tube designs. These break the single big jet stream into many smaller, higher frequency streams. Higher frequencies don't travel as far, attenuate faster. Plus, using acoustic liners, sound-absorbing materials inside the engine nacelle helps soak up noise.
Finally, the source touches on emissions. Sounds like progress is being made there.
Yes, definitely. Big focus on reducing NOx, oxides of nitrogen. Advanced combustor designs, like the TAPS combustor mentioned, aim to premix fuel and air much better before burning.
Why premix?
Allows leaner burning, less fuel relative to air, which means lower flame temperatures, lower temps, significantly reduce NOx formation. Plus, just overall improvements in engine efficiency help cut down other stuff like carbon monoxide and unburned hydrocarbons.
Wow, what an incredibly detailed journey through how engines breathe. From simple air scoops to, well, thrust vectoring nozzles.
Absolutely. It really is fascinating, isn't it? Seeing that critical balance, efficiently getting air in, mixing fuel, making immense power, and then safely getting the exhaust out. And such different but equally clever approaches between recips and turbines.
It really is. So as everyone listening goes about their day, maybe consider this. With this constant push for more efficiency, lower environmental impact in aviation, what might the breathing systems of future aircraft engines even look like? Will we see even more radical inlet designs, more sophisticated ways to use exhaust energy? maybe totally new combustion or noise reduction ideas. It's definitely something to think about.
Indeed. And if any specific part of this deep dive really caught your interest, maybe the different turbo controllers or the latest noise suppression tech, we absolutely encourage you to explore further. There's a huge world of engineering out there.
This has just been scratching the surface, really, of how these amazing machines take their breath.